Hello, Algebra 2 students. Today we will finish Chapter 12 by doing 12.5 notes, use recursive rules with sequences. So in section 12.2, we first learned about an arithmetic sequence and we learned to write a rule for an arithmetic sequence. And the formula that we used was a sub n equals a sub 1 plus n minus 1 times the common difference. So it was this formula that we used. D was the common difference. That is known as an explicit equation. So, an explicit rule is a rule for a sequence that gives the nth term as a function of the term's position number. So, for example, if you see where I wrote the definition for explicit rule, the nth term is equal to 3 times n minus 2, where n represents the position number, whether it's 2 or 4. Like if I asked you to find the 7th term, it'd be 3 times 7 minus 2. If I asked you to find the 50th term, it'd be 3 times 50 minus 2. That's what it means by as a function of the term's position number n. In 12.3, we learned to write a rule for a geometric sequence, and that formula was the nth term is equal to the first term times the common ratio to the n minus 1, where r is the common ratio. In this section, we are going to talk about recursive rules. And honestly, recursive rules are actually easier than explicit because there's not that much work involved. So here's what a recursive rule is. A recursive rule is a rule for a sequence that gives the beginning term or terms of a sequence and then gives a recursive equation that tells how the nth term which means the next term is related to one or more preceding terms. Now, it probably doesn't mean anything to you what I just said, but a recursive rule has two parts. So here's what the parts are like. So one part, the part that you must have is what the first term is. So that part, list it right away. The next part is what is the next term? Oh, I did not even mean to write that. I meant to look at it in this example. So sorry. So here the first term is 4 and the next term is equal to, now what in the world is this right here? Oops, keep doing that. So what does this mean? We know that this means the left side means nth term, but what does this mean? That means the previous. Because if the next term, this is the nth term or the next term, same thing, then if n represents the next term, then n minus 1 has to be the one before it. So the previous term. So a sub n minus 1 always refers to the previous term. That makes sense. So think about if you replace n with 2, 2 minus 1, that would be the first term. So means the previous term. Super important that you remember n minus 1 means the one before n. That makes sense, though. It's n minus 1. So I'll show you how to use the recursive rule. So in example 1, the recursive rule says, or the directions say, write the first 6 terms of the sequence. So looking at example A, the first term is equal to -2. The next term, so I'm going to write it in words what this actually means. You know what this means. The first term is -2. The next term is always equal to the previous term plus 3. So you have to add 3 to the previous term. So let's list the first 6 terms of the sequence. We know the first term is -2. Shouldn't get that wrong. I highlighted it in green. So what's the second term? The second term is going to be whatever the first term was, which was -2 plus 3 added to it. So if I wanted to show my work, I'm going to show my work here. So it'd be -2 plus 3. Okay. But I'm just going to write the answers. So let's just write the answers. It's really easy and you should be able to do it. So writing the answers, we know the first term is -2. The next term is -2 plus 3 because it's saying add 3 to the previous number. Well, the previous number was -2. So -2 plus 3 is 1. Now take that answer, which is 1, and add 3, which is 4. Take 4 and add 3, that's 7. Take 7 and add 3, that's 10. We need one more because it says first 6 terms. And there we go. It's really not that hard to use. Just look at the previous number and either add or subtract if it's an arithmetic recursive rule. The next one, example B, is a geometric. How do I know? Because I don't have a plus or a minus something. So this one is geometric. So this one, the first term is 32. And here's the next term is 1/2 times the previous number. So, I keep doing it. I don't know why I keep doing the same thing over and over again. So next term equals 1/2 times the previous number. Because remember, anything with a subscript n minus 1 means previous number. So 32 is the first term. The next one would be 1/2 times that. So 1/2 times 32 is 16. The next one is 1/2 times 16, which is 8. 1/2 times 8 is 4. 1/2 times 4 is 2. And 1/2 times 2 is 1. And there's our 6 terms. Okay. Now, in example 1, I gave you the recursive notation. I didn't tell you to write it. Here are the equations for the arithmetic and geometric sequences. So for an arithmetic sequence, you always have to have these parts for it. So, like I said, always have the first term. And then the second part is the next term is always equal to the previous number plus the common difference. So the D can be a positive or negative 1, but that's exactly how you would write an arithmetic sequence using recursive rules. For a geometric, you have the same first term, but the second part is the nth term or the next term is equal to R, which is a common ratio, times the previous number, where R is the common ratio. So it kind of tells you, and we're going to use that model to do example 2A and B. So example 2, we need to first figure out if it's arithmetic or geometric. So we need to go and figure that out. And so this looks like it can be an arithmetic, but let's figure it out. So let's try for arithmetic. So if we want to see if it's arithmetic, we take the last term minus the previous. So 88 minus 68 is 20. 68 minus 48 is 20. 48 minus 28 is 20. Let's go all the way to the end just to make sure that they're all the same number, 20. So we know it's arithmetic. So since we know it's arithmetic, let's write it down here. Then we need to use the arithmetic sequence. So we need to use this. So we need to write the first term. The first term is equal to 8. So remember this recursive has two parts. Second part, the next term, is equal to the previous. You don't put the number 8 there. You just put this as your notation representing the previous number plus the common difference. And the common difference was 20. And then when I ask you what's your answer, you don't say one of those. You have to box up the whole thing because you have to include both parts. So that is your recursive rule for that particular arithmetic sequence. Okay, the next one definitely doesn't look like it's arithmetic. First of all, there's fractions involved. So I would suggest that we figure out what the common ratio is if it's geometric. If it's neither, we still would have to write a recursive rule, but I would never do that to you. So I'm going to do the work over here. So I'm going to take 64 over 25 divided by 32 over 5. Okay, so that is 64 25ths times 5 over 32. 32 goes into 64 twice, and 5 goes into 25 twice. So that's 2/5. So this one gave us 2/5. Let's do the next one. The next one is 32/5 divided by 16. Oops. So that's 32 fifths times 1/16. 16 goes into 32 twice. That also is 2 fifths. So I think we should try multiplying by, well, you know what? We're going to do the remaining one. So 16 divided by 40. Divide top and bottom by 8, and that gives me 2 fifths. Ooh, so far they're all 2 fifths. And the last one, 40 divided by 100. Zeros cancel. Divide top and bottom 2 fifths. Woohoo! All that work. R is 2 fifths. So we know it's geometric. So geometric. This is the first term. So let's write our two parts. The first term is equal to 100. The next term is always equal to whatever the common ratio is. And in this case, it's 2 fifths times the previous number. And the previous number is represented by a to the a sub n minus 1. So there is your answer. I like these because you don't have to do that much work. I mean, the first term's easy. And the second one is just how to write it correctly. Now, can you put the a sub n minus 1 first, then put a dot, then 2 fifths? You totally can. It's up to you. Okay. Our last example, example 3. A mosquito population in a controlled laboratory condition is estimated to be about 500. Each day, so the initial population is 500, so this is our first term. Each day, an additional 100 mosquitoes are hatched. The population also declines by 85% every day. So each day an additional 100 mosquitoes are hatched. The population also declines by 0.80 or by 85% every day from pesticide and other natural causes. Here's the thing to remember. If the population decreases by 85%, even though you get 100 new ones, like so you have 500 mosquitoes, then you get 100 more. So the next day you would have a certain number, but it also declines by 85% every day from the pesticide and other natural causes. So if it's going to decline by 85%, then 15% will remain. So 15% mosquitoes remain. And that's 0.15. So here is how you do this particular one. So the first part should be easy. So part 1 is always giving our first term. Our first term is the initial amount, which is 500. But then our next term is equal to 15% of the previous number. So, and the reason why is because only 15% remains. So you need to multiply the previous number. And in our case, the previous number would have to be 500. We don't put the 500 there. We represent the previous number by that because it's going to change every time. Plus 100 is hatched each day. So here's how you would do it as far as math goes. You would take a calculator. So it says find the number of mosquitoes after the 5th day. Well, let's figure out the first day is 500. So that's day 1. Okay, day 2, here's how you do day 2. You would take that 500, you would multiply it by 0.15 because that's what our rule is telling us to do. It says take 0.15 times the previous number. Well, the previous number is 500, and then add 100, and you get 175. So that's day 2. For day 3, you take the 175, multiply it by 0.15, add 100, and you get 126.25. For day 4, take 126.25, multiply it by 0.15, add 100, and you get 118.9375. Okay, it asks us for the 5th day. Now take that number, 118.9375, multiply it by 0.15, and add 100. You get 117.840625. And now what if I said find it after the 40th day? You can't do this all the time. And there's another way to do it. I'm going to show you on a calculator, but I will show you after we finish up this problem. So at this point, let's just approximate it. So that's approximately 117 mosquitoes. So on the 5th day. Describe what happens to the number of mosquitoes over time. Well, this is the one I'm going to show you on my graphing calculator. So basically, what it does is it stabilizes to 117.65. And those are our notes for today and the rest of the notes for Chapter 12. Have a great day, Algebra 2 students.